Welcome once again, and today we are going to start with the new chapter, that is nets and filters. So this is the new chapter we are going to start today from topology. So before moving on to nets, we will have to understand directed sets. What are directed sets? How are they being constructed? So I'm starting with the definition of directed set, and we will use binary operation for that too. So here I am starting with the definition of directed sets, and then we will give some examples. We will understand properly directed sets before moving on to the topic of nets. So let D be a non-empty set. Let D be a non-empty set and greater than or equal to, I'm just having this greater than equal to as a notation. It is not in its usual sense as we use this symbol for 5 greater than or equal to 4. We are not using this symbol in this sense. We are using this symbol just as a notation. So add greater than or equal to be a binary operation. Be a binary operation defined on D and satisfying following axioms. So what are these axioms that will make this set D together with this binary operation greater than or equal to a directed set? These are: number 1, M is greater than or equal to M for every M belonging to D. So every element M of this set D satisfies that M greater than or equal to M, where this greater than or equal to this binary option will be defined as per given. The second axiom is that if M is greater than or equal to N and N is greater than or equal to P, then M is greater than or equal to P, where these M, N and P, they are members of the set D. Thirdly, the third axiom: for every M, N belonging to D, you take any two elements from the set D, there always exists a third element P from the set D such that P greater than or equal to M and P greater than or equal to N. If these three axioms, these three properties are satisfied, then we say that D together with this binary operation greater than or equal to is a directed set. This symbol greater than or equal to will be taken sometimes in its usual sense and sometimes just as a notation for the binary operation. And if you don't want to read it as greater than or equal to, you can read it as follows. So that means M follows M for every M belonging to D. If M follows N and N follows P, then M follows P. And if M and N are any two elements of D, there exists P belonging to D such that P follows M and P follows N. So this is the definition of directed set. And then we will give some examples of directed sets, and the binary operation may be greater than or equal to in its usual sense, or it may be something else. So in the first example 1, you can say, you can take your D as the set of natural numbers or the set of real numbers and take greater than or equal to as in its usual sense, and then this will form a directed set. Why? Because number one, for every m belonging to n or for every m belonging to R, we know that m is greater than or equal to m. We know that. It is here, this is used in its usual sense. So here I am using it like that, 5 is greater than or equal to 5. Or for if you are talking about R, then you can say under root 2 is greater than or equal to under root 2. You can say 5 upon 4 is greater than or equal to 5 upon 4. So for every m belonging to n or for every m belonging to R, m is greater than or equal to m when this symbol greater than or equal to is used in its usual sense. Secondly, for every m, n, p belonging to n or belonging to R, m greater than or equal to n and n greater than or equal to p implies m greater than or equal to p because of the transitivity of greater than or equal to. If a natural number is greater than or equal to another natural number and this natural number is greater than or equal to another natural number, then the first natural number will definitely be greater than or equal to the last natural number. This is the transitivity of greater than or equal to in usual sense. Similarly, for the set of real numbers. Thirdly, for every m and n belonging to the set of natural numbers or the set of real numbers, take p to be maximum of these two m and n, then definitely your p is greater than or equal to m and your p is greater than or equal to n. That means all the three axioms, all the three properties are being satisfied. So the set of natural numbers together with binary operation as greater than or equal to in its usual sense, or the set of real numbers with the binary operation greater than or equal to in its usual sense, they are the directed sets. So n greater than or equal to is a directed set, R greater than or equal to is also a directed set. So this was the first trivial basic example of a directed set. Then we will move on to some other examples. So let us have another example. Let X be any non-empty set. Consider your power set of X, means the set of all subsets of X. Take it as D, and this greater than or equal to this binary operation, take it as subset of. Take it as subset of. So here your D is this set and your binary operation is this operation, subset of, and let us see whether if it is a directed set or not. So number one, for every element belonging to D, here your D is the power set of X and members of power set of X are sets. So for every set A belonging to power set of X, we know that A is a subset of A. That means A follows A. So the first axiom is clear. Secondly, if A is a subset of B and B is a subset of C, that means if A follows B and B follows C, then it is clear that if A is a subset of B and B is a subset of C, then A will be a subset of C, where these ABC are members of power set of X. So the second property is also satisfied. Thirdly, let A and B be any two members of power set of X. Take C as A intersection B. Then C is a subset of A and C is a subset of B. And C, that means A intersection B, is also a member of power set of X. That means for every A, B belonging to this set, you are always having a third set C in the same set, power set of X, such that C follows A and C follows B. So the third property is also satisfied. So your power set of X together with the binary operation subset of is a directed set. Even if you take here superset of X, no problem will be there, because here A is a superset of A is trivially true. If A is a superset of B and B is a superset of C, then A is a superset of C is once again true. If A, B are any two members of power set of X, take your C now as A union B. It also belongs to power set of X, and now C is a superset of A as well as a superset of B. So once again all the properties are satisfied. So power set of X together with this operation superset of is also a directed set. So we have given examples with the binary operation as greater than or equal to in its usual sense, and here the binary operation greater than or equal to is not in its usual sense, but it is subset of or superset of. Another thing, if X tau is a topology where X is a non-empty set, X tau is a topological space. If X belongs to X, then the system of neighborhoods of X, that means the collection of all neighborhoods of X with subset of, this is also a directed set, because of the same reasons that we have given in the previous example. If N is any neighborhood of X, that means N is an open set containing X, then N is a subset of N without any doubt. It is always true. Secondly, if there are any three neighborhoods N, M, P of X such that N is a subset of M and M is a subset of P, then N will always be a subset of P, because N and P may be the neighborhoods of X, but still they are the sets. And in set theory we know that the transitivity holds for the binary operation subset of. If N is a subset of M and M is a subset of P, then N is also a subset of P. So second axiom is also satisfied. Thirdly, if N and M are two neighborhoods of X, then N intersection M, that means P, is also a neighborhood of X. Intersections of two neighborhoods of X is also a neighborhood of X. So this P, that means N intersection M, is also a neighborhood of X, and P, that means N intersection M, is a subset of N and is also a subset of M, that means P follows N and P follows M. So all the three properties are once again satisfied. So that means your neighborhood system of X along with the set subset of is also a directed set. And now we are moving towards a very interesting property of directed sets, and let us see what it is. So here you can say it is a property, it is an article, it is a theorem, whatever name you want to give you. I am writing it as an article. Let D1 with greater than or equal to 1. This is just a symbol for binary operation. Let this and D2 greater than or equal to 2 be two directed sets. Then D1 Cartesian products with D2 and binary operation greater than or equal to is also a directed set, where this binary operation greater than or equal to is defined as now this operation will be defined on this set D1 cross D2, and the members of D1 cross D2 are the ordered pairs having first member from D1 and second member from D2. So that means M1, M2. So this is an element of D1 cross D2. So I am defining M1 cross M2, M1 M2 sorry, is greater than or equal to N1 N2 if now M1 is a member of D1, N1 is also a member of D1. So M1 and N1 will have binary operation of D1, that means greater than or equal to. So if M1 is greater than or equal to 1 N1, and similarly your M2 is greater than or equal to 2 N2. So this is how we have defined this binary operation greater than or equal to on the Cartesian product of two sets D1 and D2, and now we will show that this D1 cross D2 along with this binary operation is also a directed set. And for that, what we will have to do, all the three axioms we will have to show that they are holding here very well. So let us see these properties one by one on D1 cross D2. So the first of all, take any arbitrary element M1 M2 belonging to D1 cross D2, and what you want M1 M2 is greater than or equal to M1 M2. You have taken an arbitrary element, and if you show this, that means this holds true for every element M1 M2 of D1 cross D2, and it holds true. Why? Because by definition of this binary operation, it will hold if your M1 and this M1 is greater than or equal to 1 M1, and it is true because M1 is coming from D1 and this is the binary operation of D1, and D1 along with this binary operation is already given to be a directed set. So the first property of directed set of D1 with this greater than or equal to 1 will give this result to us. And similarly, this M2 is coming from D2, this M2 is coming from D2, and by our definition of this greater than or equal to, this M2 should be greater than or equal to 2M2, and which is once again true because this M2 is an element of D2 and greater than or equal to 2 is the binary operation of D2 under which D2 is a directed set. So the first property of directed set from there will make this statement true. Now move on to the second axiom, the second property. Second property, let us have three elements. Let M1 M2, N1 N2, P1 P2 be three elements of D1 cross D2 such that your M1 M2 follows N1 N2 and your N1 N2 follows P1 P2. Now what we have to show that M1 M2 follows P1 P2. If the second property we want to show that it is true. Now we will move one by one. First this, and then we will combine the results. So this implies by the definition of this greater than or equal to that M1 greater than or equal to 1 N1, comma M2 greater than or equal to 2 N2. So here I have applied the definition of this binary operation greater than or equal to, and the same binary operation greater than or equal to is here. So we can apply the same results here. So what you will get from here, that your N1 greater than or equal to 1 P1, comma N2 greater than or equal to 2, P2. Now look into this one and this one. M1 follows N1 under this operation and N1 follows P1 under the same operation. M1, N1, P1 are the elements of D1 and this operation, this binary operation is for D1, which makes D1 a directed set. So under the property, second property of directed set of D1 greater than or equal to 1, you have your M1 follows N1 and N1 follows P1, means your M1 follows P1. Similarly, you can apply the same result here to get your M2 greater than or equal to 2, P2. Now once again combine these two. Combining these two by using the definition of greater than or equal to, what you are going to get that M1, M2 is greater than or equal to P1, P2. So that means if M1, M2 follows N1, N2 and N1, N2 follows P1, P2, then M1, M2 follows P1, P2, and so the second property holds very well. Now we are moving on to the third property, and after proving that the direct D1 cross D2 with this new defined binary operation will become a directed set. So let M1, M2, N1, N2 be two elements of D1 cross D2. This means your M1 and N1 are coming from D1. Your M1, N1 are coming from D1 and your M2, N2 are coming from D2. Now M1, N1 are members of D1 and D1 with binary operation greater than or equal to 1 is given to be a directed set. So therefore there exists P1 belonging to D1 such that your P1 follows M1 with this greater than or equal to 1 and your P1 follows N1 under the same binary operation. Similarly, M2 and N2 are the members of D2 and D2 with this binary operation is given to be a directed set. So therefore, by third property of directed set, there exists some element P2 in D2 such that your P2 is greater than or equal to 2 M2 and P2 is greater than or equal to 2 N2. Now look into this and this together and use the definition of your binary operation greater than or equal to. What you will get? You will get P1, P2, the ordered pair is greater than or equal to M1, M2, and now apply the same result on these two to get your P1, P2 follows N1, N2, and this P1, P2, this is an element of D1 cross D2 because your P1 is coming from D1 and your P2 is coming from D2. So if you are having M1, M2 and N1, N2 from D1 cross D2, then there exists P1, P2 in D1 cross D2 such that P1, P2 follows M1, M2 and P1, P2 also follows N1, N2, and that makes your D1 cross D2 together with this binary operation greater than or equal to a directed set. So in this video I have defined directed sets, we have understood the examples. So this is the first base for your nets and filters topic. So better if you keep this concept clear in your mind. In the next video we will understand what are nets, what is their convergence, what type of nets are there, etc. and so on. Till then, thank you once again.